Going to look at differentiating exponential and logarithms, page 84, example 9 of the textbook. First of all, for example 9, we have to find dy by dx for each of 4 functions. We're going to start off with a, the function that has y equals e to the sine x. Now we're going to use the chain rule here, and we're going to place u as sine x. So what that means is y is just e to the u. Now if we differentiate these, dy by du is just e to the u, because we found that if we differentiate the exponential function, we get itself. And if we differentiate u with respect to x, if we remember the differential of sine is cos. Now from the chain rule, we know that dy by dx is dy by du multiplied by du by dx. dy by du is e to the u, so that's e to the sine x. And we're going to multiply that by cos x. And we note that as cos x e to the sine x. And that's it, that's dy by dx. For part b, we have to differentiate this function y equals ln of 1 minus cos x. Again, we're going to use the chain rule with u equal to 1 minus cos x. We now have that y equals ln of u, which looks much nicer. And we have that we can now differentiate them both. So du by dx, differential of 1 is nothing, differential of cos x is minus sine x, but one negative differential, so that's going to be sine x. And differential of y with respect to u is 1 over u, which in this case is 1 over 1 minus cos x. So dy by dx is the product of these, so it's sine x multiplied by 1 over 1 minus cos x, which is sine x all over 1 minus cos x. And that's your differential there, again using the chain rule. Part C looks a little bit more complicated. As you can see, I've got here e to 3x multiplied by tan x, so I'm going to use the product rule. If I have u equals e to the 3x, 3 there, and v equals tan x. If I differentiate both of these, du by dx is 3e to the 3x, and dv by dx is sec squared x. If you're a bit unsure how I got this 3e to the 3x here, you can use the chain rule, substituting in for 3x, and if you differentiate 3x you get 3, and differentiate e to the u you'd get e to the u, so you get 3e to the 3x. Okay, so the differential dy by dx is u multiplied by dv by dx, so that's e to the 3x multiplied by sec squared x. Then I'm going to add to that du by dx multiplied by v, so that's 3e to the 3x multiplied by tan x. These two have a common factor of e to the 3x, so I can take e to the 3x out, and then it's sec squared x plus 3 tan x. And that's my differential there. Okay, part D looks like the hardest thing yet. It's one function divided by another one, so we're going to use the quotient rule, which is when you've got some function over another one. So in this case, our u equals ln sine x, and v equals ln cos x. Okay. Now the thing is, I'm going to have to differentiate both of these, and they look a bit disgusting to differentiate. So you might want to use the chain rule to differentiate both of these. Well, now I've already used the letter u, so I might use the letter a, for example, and say that u equals ln of a, where a equals sine x. So using the chain rule, du by dA is 1 over a, dA by dx, looks like a u there, dA by dx is cos x. And if I multiply these together to get du by dx, which is what I want up here, du by dx is going to be cos x over sin x. Okay. Similarly, over here, if I say v equals ln b, where b equals cos x, then dv by db equals 1 over b, db by dx is minus sin x. Okay, and then so dv by dx is minus sin x over cos x. Okay, so if I remember my quotient rule, to differentiate it, I'm going to have v first, viv goes first, and then du by dx, and then I'm going to subtract u dv by dx, and that's all going to be over v squared. So I'm probably going to need a bit more space. I'm going to move some of this stuff across. Okay, so I have dy by dx is going to be v, which is ln cos x, multiplied by du by dx, which is here, cos x over sin x, subtract u, which is ln sin x, multiplied by minus sin x over cos x, which is dv by dx, and that's all over v squared, which is ln cos x all squared. Okay, this looks pretty messy and nasty, but I'm just going to sort it out a little bit. I don't like having this sort of fractional thing here and here on the numerator, so I'm going to take those things to the denominator. So at the moment, this first term is over sin x, and the second term is over cos x. So if I want to take sin x and cos x to the bottom, I'm going to have to multiply the first term by cos x and the second term by sin x. If I did that and rearrange, I'm going to get that equals cos squared x, because I had the cos x and I multiplied it by cos x, ln cos x, minus sine squared, but it's actually now plus sine squared, careful with that, because we've got a minus here and a minus here, becomes positive, ln sine x all over, well previously I just said it over ln cos x all squared, but I've also taken the sine x and the cos x to the denominator. And this rather large looking thing is my differential. On example 10, page 85, we're asked to find these integrals, starting off with this one I've shown here. Now this might look really disgusting and something that looks much too complicated to integrate. But what we can notice is that here you've got tan x, and I know that if I differentiate tan x, I get sec squared x. So it's looking quite good. So let's try just considering what would happen if I had e to the tan x, and if I differentiated that using the chain rule, if that's, let's say y equals this, then that's e to the u if u equaled tan x. If I differentiate that, dy by du equals e to the u, du by dx is sec squared x. This e to the u is e to the tan x, so dy by dx is the product of these, which is sec squared x tan x, e to the tan x, e tan x. Okay, now that is good because that's the exact thing that I've got up here. So I know that if I differentiate this thing, I get this thing, which means if I integrate this thing, which is the reverse differentiation, I'm going to get this. So the integral of this is e to the tan x plus some constant of integration. Okay. Part B looks a little bit more complicated because it's got a division in it, it's a fraction, you might think it's a bit more tricky, but whenever it's got this, we're going to be thinking of ln. So, if we considered what ln of the denominator might be if I differentiated it, so if y was that, then dy by dx, using the chain rule, will be cos x multiplied by 1 over 1 plus sin x, which is cos x all over 1 plus sin x. So I know that if I differentiate this, I get this. Therefore, if I integrate this, I will get this. So I know the integral of my function here is ln 1 plus sin x plus some constant of integration. So each time you consider what you think it might be, differentiate it, see if you get the right function, and then add your constant of integration.